Okay, so good morning, everybody. And so today I will talk about identifying quantum phase transition with adversarial neural network. And first of all, I want to thank the organizer for organizing this nice workshop and for giving me the opportunity to present my work. So to present myself, I'm a postdoc. I'm doing a postdoc in the group of Maciej Lewenstein at ICFO in Barcelona. And the work that I will present today has been done in collaboration with two people, Patrick Wimbley, which is the PhD student that did most of the calculation in this work, and Peter Wittek, which is here in the audience. And I will start with the outline of the talk. So in this talk, I will start with a general introduction on machine learning and phase transition and explain how we want to combine them. Then I will introduce the method of interest, which is this domain adversarial neural network, and explain why we believe that it's a good method to classify phase transition. And then I will benchmark it on several examples from like quantum models, like where we see quantum phase transition, and use this algorithm to characterize them. And finally, I will go to the conclusion and the outlook of this talk. So let's start with the introduction. So in the introduction, I want first to talk to phase transition, and what is known is that the phase transition is an important topic in condensed matter. And here the idea is to really find a kind of, in physics, to find an order parameter to characterize the different phases of the system. And there are several examples already at the level of non-interacting systems where this is interesting. For example, in the interplay with disorder that can lead to Anderson localization, or in the case of topological insulators, where it can lead from like the disorder can really give rise to a transition from a topological system to a trivial phase. And also when we go to the interacting system, the classification of the phases can already be complex at the level of the mean field. But if you add like interaction in disorder, this could lead to many body localization that is like kind of difficult phase to characterize. And so the natural question that arises in this kind of conference is whether a machine algorithm can help us to recognize these phases. And here I do a brief review of this machine learning technique for image classification. Imagine that you have like numbers like as this MNIST database, and you want to classify them. You can do two things. The first thing would be supervised learning, where you have like the source data that are these numbers that are labeled, so 0 is a 0. And then you have like new data, and you want to predict this unlabeled data. Or you can do unsupervised learning, as it was discussed already in the talk of Alejandro, where you have like unlabeled data, and you want to try to find some structures, some clusters in the data that allows you to say something about this data and the structure. And this is, for example, what you can do with TSNE if you use the MNIST data. What about phase transition? So there are several works where they use like supervised learning to try to characterize phase transition. So it can be done with fully connected neural networks, for example, on the entanglement spectrum of the system, or directly with convolutional neural network. And there are other works where they did like unsupervised learning, for example, with principal component analysis or this W-shape. And what about our work? In our work, we wanted to use like state-of-the-art machine learning techniques, and we wanted to derive directly the whole phase diagram with this method that is called domain adversarial neural network. And the main message of this work is that we really wanted to draw like that we take the ground state or the approximation of the ground state that you obtain with your preferred technique, and without any ad hoc engineering, we want to give that to the neural networks. And we want this method to find the phase transition point without any ad hoc engineering. And we benchmark this method on several paradigm models that are coming from quantum phase transition. And so the idea is really, I take my Hamiltonian, I take the ground state of it with the method that I have, and then I use this algorithm to find the phase diagram. Okay? What about the methods? So this domain adversarial neural network. So to come back to that, I want to introduce the idea of this classification with images first. If you take the images, for example, the MNIST, and you want to do classification, you will pass through a feature extractor that can be typically a convolutional neural network. And this gives you a feature space that allows you to do classification with a fully connected neural network. And if you do that, it's very nice, and you can train it with this like kind of backpropagation, gradient descent. And what you are able to do now is to really like that if you have like a new image of a tree that was, for example, not in the training set, this algorithm will allow you to predict this value of the tree. But now you say, okay, I take like data that are very similar but with different backgrounds, with different statistics, and I pass it to my trained network that I did before. And if I do that and I put an image of a tree that is now with this different background, the machine is totally failing, so it's not able to predict it. So what people propose to solve this problem is this, one of this method is this domain adversarial neural network, and I will explain it here. So the idea is that you have like a source data set that is labeled, so your MNIST database, for example, and you have a target that is not labeled, so you don't have the label. And you do two things. You pass through your feature extractor and you obtain the feature space. Then you do the normal classification on this source data set, but you also do another task, which is this domain classifier. This domain classifier, what it is doing, it's really saying this data set is from the source or from the target, okay? And you do the training of this loss function that you have here. And for the loss function of the classifier, it's really the normal gradient descent that you have, like backpropagation. But in the case of the domain classifier, you want to do something different. So in the part of the fully connected neural network, you really do gradient descent. But when you pass through the feature extractor that can be this convolutional neural network, what you do is like gradient reversal. And so the main idea of this is that you want somehow that this feature extractor is trying to like make the domain classifier working not so good. No? So you want somehow that the data that are coming from the source and the target are very similar in the feature space, okay? So from the same cluster. And so this should help for the classification. And now after the training, if you do that and you look at the data, so if you take a tree that was non-seen and that was of the type of the source set, then you will obtain this tree. And also now if you take this tree from this target set that has no labels, now you will find that you can really recover this label. So it's very nice. And we wanted to apply that. A last thing that I want to say is that one very nice thing that you can do also is to look at the feature space that you have here. And from this feature space, you can really look at the clustering of the data. So you pass your data through, and then you can use your favorite method unsupervised to see like how the clusters are formed and try to find some information about the clustering of the data. So what we wanted to do for the physics part is really to imagine that you have an Hamiltonian and you have a method that you have for approximation of the ground state, and you know that this Hamiltonian is depending on several parameters, and you also know that there are two phases in your phase diagram. And you know that deep in these phases, you know the value of this thing, and this will be somehow for us this source set, okay? And then the rest of the parameter space and the ground state that you obtain will be your like target set. And so we want to use this algorithm to try to help us to find phase transition. And so at the end of the day, what we hope is that the algorithm will really be able to find like the phase transition point in the system. So now I will talk a bit about different benchmarks that we did in our recent works. And the first one is the Bose-Hubbard model, which is a model of interacting bosons on a lattice. And here we like model it with like 10 building Hamiltonian with nearest neighbor hopping and on-site interactions. And what we do here, so the approximation of the ground state that we use is like the Gutzwiller coefficient. So we have the Gutzwiller coefficient, and we choose the label states, and for that we choose this line of the phase diagram, and this is what we give as a source set. And so we do this characterization, and the unlabeled state is the rest of the phase diagram. And so what we ask to the machine is to classify them, and the results are shown here. So this color plot that you see is really the output of the neural network. The red value is what is predicted as Mott insulator. The blue value is like what is predicted as superfluid. And what you see is that we reproduce the very nice mode lobes. And also the results are coherent with other analyses that you can do with compressibility that are presented here. And also what I can say is that at the tip of the lobes, we can have analytical solution. And this analytical solution is very matching to what we obtain from our learning algorithm. Then we studied another example, which is this SSH model with disorder. So this is a model that is known to be topological. So it's a model of spinless fermions with nearest neighbor hopping, but this nearest neighbor hopping is staggered. So you have J1, J2, J1, J2 for the nearest neighbor hopping. And this model is known to have a topology when a J1 is smaller than J2. But here what we wanted to study is the situation with disorder. So we add disorder to the system on these different hoppings, and we want to see how the phase diagram looks like. And so this is known from this paper that there is a phase transition when I increase the value of disorder. So I can pass from a topological phase with winding number equal to 1 to a topological phase with winding number equal to 0. And actually, this week we will have also a talk on Pietro that will discuss about the possibility of observe that in experiments. So it's something very interesting. And so what we are feeding to the machine here is we take this Hamiltonian here, it's non-interacting, and we we diagonalize it exactly. And what we feed here is all the occupied states. And what we give as source states are these states without disorder, because there we can really label them analytically. And the labeled states are the states with disorder. And then we can look at the results of the training. And in the case of so here what I show is really the output of the neural network of the classifier for different strengths of disorder. So what we are seeing is that when we increase the disorder, we see that the phase transition point is changing. And actually, these results are in accordance with other methods, such as winding numbers that can be obtained in real space. So finally, I want to talk a bit about a work that is in progress, in unpublished, where we are working with Christian Rorolin, and we are working on the problem of many-body localization. So the idea is that we have a 1D system that is now fully interacting of spins. So it's Heisenberg model, where we have the spin-spin interaction plus on-site sigma z term that is random. And this model is known to have kind of a transition from a delocalized phase to a localized phase. And so here we wanted to benchmark that algorithm and see whether we can do something in this model that is really interacting with an interacting ground state. And so what are the inputs here? It's really, again, the eigenstates from the exact generalization. And the source states are states that are deep in the phase. So for example, here in the localized phase, where it's the energy of this eigenstate, and deep in the many-body localized states. And so what we were wondering is whether we can reproduce this kind of curve shape and also characterize the phase transition. And that is what we did. So here what I show is some results for different system size. And what you see on the left is one of the typical order parameters that is shown in this many-body localized paper, where you show the level statistics for 100 disorder realization, its average on 100 disorder realization. And what you see on the right is so it's preliminary results, but you see the neural network output for different value of the disorder. And I mean, one striking thing is that for the same number of disorder averages, you see already that the neural network output is much cleaner than what you see from the level statistics. Here you see that you have a lot of wiggling, and the error bars are much bigger than in the case of the neural network output. And also, I think one thing that for me is very striking is the fact that we have such a nice plateau that is appearing here and also here in this curve. And this is something that we are investigating for the moment to understand better how the algorithm is really helping us to have like such a nice plateau. And also what we want to do in the future is to use these three different curves to do some kind of scaling and to try to give information about like the thermodynamic limit, the phase transition at the thermodynamic limit. And finally, I mean, last but not least, to show one of the last results that we have is, I mean, it's really a comparison with the plot that we saw here, where you can really see like the kind of transition in terms of the disorder here and in terms of the energy of the states. And we feed these states to the network, and we asked him to reproduce it for a given system size. As you see that qualitatively, let's say we recover this like curved shape that you should obtain for such kind of transition. And I mean, with that, I will go to the conclusion and the outlook of the talk. So I hope that I've convinced you that there is an interest to use this kind of state-of-the-art machine learning technique, and here in particular this domain adversarial neural network, to like trying to characterize phase transition and quantum phase transition. And I mean, the main message of this work is that we really want to use like directly the approximation of the ground state or the ground state, and this without any ad hoc engineering to feed it to the neural network. And so I showed some example where we benchmarked this method on several paradigmatic models, and we showed that the results that we see are in good accordance to the results obtained with normal order parameters. And okay, if you look at the paper, we also show that it allows to give you some clue of the presence of new phases in the system. And finally, I want to mention that because we are using these convolutional neural networks, we believe that this method is scalable for like interacting system. And this is, for example, the case for this many-body localization. And with that, I want to thank you for your attention, and thanks also for the funding.
Thank you, Alexander. Questions?
How sensitive do you feel your techniques are to the feature distribution between your labeled and your unlabeled data sets when you start? So if you go to your earliest slide and you show a featured data set and an unfeatured data set of numbers, so unlabeled data set.
So you say here?
No, at the very early part, you show the numbers. You have a table with your labeled and your there.
Yes.
If you start and your feature distribution between your labeled and your unlabeled are orthogonal or not overlapping very much, what's your intuition? Does that matter in this instance, or does it not?
So I mean, okay. So I mean, the role really of this this gradient reversal, and we can see that when we really go like with this unsupervised method like TSNE, we can really see how the data are, for example, if you do like only transfer learning. No? So you start with your data, and you look at how the data cluster in the feature space, for example. No? And what you see is that in the case of not using this kind of domain classifier, we really see like two distinct clusters that are coming from like data from the source sets and from the target sets. And this is, in a sense, my interpretation why you cannot really like do a nice classification, because you have two different clusters that are appearing. The nice thing of this algorithm is that in principle, when you trend it, what you should see is that these two clusters are now one cluster.
So if you don't, you iterate, you find other data. What do you do if your results are not meeting your expectations, or that in this instance, this is very intuitive, this data? What if you start with data sets that you're really doing model discovery and you just don't have strong intuition yet, which is why you try to use unsupervised learning to begin with?
But that's, so I mean, these kind of methods, I think it's pretty good in the case that you know that you have, for example, a certain number of phases. And you know that deep in the phases, you know the phases, and you want to find some phase transition. And so, of course, at the phase transition point, everything is mixed up. Because what you want to do is to do classification between like source states that are deep in the phase and like your target set. But at some point, it's true that you cannot really clusterize them nicely. No? At some point, it will be like
So your initial data selection could in effect feature engineer the phase transition results, couldn't they? Or am I totally off base?
No, I would say that here it's semi-supervised learning. So in the sense that you know, I mean, you cannot say, the first thing is that you should know some phases of your system, okay? So it's semi-supervised. But what we also expect, and we have seen something like that, is that if you have a new phase that has not been seen by the system,
right.
You expect that you will have like kind of new cluster, or you have like some anomalies in your system that you can not exploit. And then you can really like try it, but the classifier will not tell you that, because the classifier tells you it's one phase or the other. But maybe if you look at the feature space, and this is what we did, for example, in our work, you see that you see like a new cluster that is appearing, that you can, for example, use like methods like k-means, say, OK, I have a new cluster, and I can classify them. The only problem of that, I mean, it's interesting because it gives you a clue, but it doesn't say to you what is the new feature. Okay? So this is, but it's still, it gives you a clue that there is something new in the system.
Thank you.
Thank you. Any other question before we go for lunch?
My question is connected with the previous one, but how many samples did you need in order to predict the phase transition, and what the ratio between number of samples and number of features do you need in order to produce a result?
So I mean, here we are in presence of deep learning algorithms. So this means that you need to have a lot of samples. So we are talking about like, So I mean, we are talking about 1,000 to 10,000 samples for the training. It's a deep learning algorithm, okay? So, I mean, the number of phases. So I mean, this algorithm is working for like the number of phases that you want. In a sense, there is no limitation in number of phases. So you can do it with, it's not limited to like 2 phases, for example. You can have n phases.
It's okay, but maybe we can continue the discussion during lunch. Thank Alexandre again and all the speakers of this morning.